Right, the third point that we're going to make, and it's very important, gravitational acceleration is always constant. And remember earlier we stated its magnitude. What is its magnitude? 9.8 meters per second squared. And then it's always acting downwards. Do you guys understand?
Yes.
Now let's state the first important point. The first important point is what? The time it takes for the projectile to go up is equals to the time it will take for the projectile to go down. Secondly, the velocity at the maximum point is 0. Third point, the gravitational acceleration is constant. Now let's model the situation of Kanye. We said Kanye is projecting a ball upward to a certain maximum height, and then the ball reaches the ground after some time. Right? Now we're going to represent that situation using position versus time graph. Secondly, we're going to denote that motion using velocity versus time graph. Thirdly, we're going to denote that motion using what? Acceleration versus time graph. Now let's start with position versus time graph. We are saying can you project the ball up and then the ball reaches the ground after some time. Now let's denote that. So we're going to have delta y here. I think you understand why we have delta y, because it's vertical projectile motion. Here we don't have delta x. Here we have delta t. So because it's position versus time graph. So we are making someone to understand where is the ball, we are answering the question, where is the ball at what time? So I can see that now the ball at some time here will be at this side. The ball at some time here will be at the maximum point. The ball at some time here. So I'm answering that question, where at what time? Now this will be the time the ball reaches the maximum, the time the ball reaches the ground after projection. So Kanye is throwing a tennis ball, is projecting a tennis ball like that. So the tennis ball will make that motion. Now this time represents the time here. Good. Now, this will be my maximum delta y. This will be my maximum position above the ground. Do you all understand? So I'll have y max. I don't want to use numerical values now. I'm going to use numerical values during my next example. So I'll call it y max. Here will be time max. Let me say it. Here it will be time max, right? This will be time total. This will be initial time, which is 0, right? According to the first key that I've given you, this T1, this is my T2. Important note to make here is that T1 is equals to T2. Are there any other questions with regards to this graph? Any other questions with regards to this graph? Then I'll wrap it, then we're going to do velocity versus time graph. But in velocity versus time graph, it is very important that you denote direction. Whether you take upward as positive and downward as negative. You need to be clear with us there. Can I wrap here?
Yes, sir.
Good. So we are still modeling the very same situation. Velocity. We are still modeling the same situation of Kanye. Kanye is projecting the ball upward. After some time, the ball reaches the ground as well. Now I'm going to have that. And instead of having my vertical axis here, I'm going to have my vertical axis at the half mast. So somewhere here. So it's velocity versus time. Here I'll have delta V. Here I'll have delta T. Good. Now I'm going to have positive velocity, negative velocity. It makes sense. Positive velocity, negative velocity. Now here I'm saying upward is positive. So you state here, upward is positive. Good. Now Can you project the ball up? The question that we are asking here is what is the velocity at what time? Remember, with position versus time graph, the answer that we're answering, the question that we're answering here was where is the ball at what time? Here the question is what is the velocity of the ball at what time? It's very important. I'm going to have some time here. I'm going to have some time here. This time will give me the maximum velocity. This is the time at maximum velocity. It makes sense because according to rule 2, we set velocity at the maximum point is 0. So this is time at the maximum. This is time at the maximum point. Time at maximum point. So I'm projecting my ball upward. Right? Now, the time it takes the ball to reach here is somewhere, it's not 0. The time is not 0. But what is 0? Velocity is 0. It makes sense, according to key number 2. And I said my upward is positive, meaning velocity, when I'm projecting the ball up, if I'm going up, velocity is a vector. Whatever that is going up will be denoted by positive. But it's very clear to make sense of it. Right? Let's say I started with a velocity of 2 meters per second. Right? 2 meters per second. 2 meters per second. Because as I go up, the velocity will diminish. So if my initial velocity was 2 meters per second, velocity will be maybe 1,8, 1,7, 1, to get my point, 1,5, 1,4, up until it reaches 0. Right? So that's why my velocity will be like that. It decreases. But this represents up. It's still going up, right? Up until this point. So this part of my graph will represent my motion of the ball from the initial point of projection up until this point, right? And we acknowledge that as I go up, my velocity decreases. As I go up, my velocity decreases up until it reaches 0 at the maximum height. Do you understand? Now, it will go down again. As it goes down again, it increases, but it increases in a negative direction. So we hear that velocity will be 0 at the maximum point, then it will increase, up until it reaches sometime here. This is the total time for my projection. I see say to what's the question?
You roll if you take negative, upwards.
Positive. Upward is positive.
So it's positive.
Yeah. No, it depends. Here I'm saying my upward is positive. Yeah. If I set precisely that upward is negative, then my graph was going to be different. But here I'm taking upward, it makes sense. Upward is positive. Up, positive. Down, negative. Good. So you understand? So this is my velocity at the maximum point. Velocity at my maximum point. And according to my key number 2, what did I say? Velocity at the maximum point is 0. It corresponds with whatever I told you. So I'm not lying. So let's make a note there. We are saying V at max point is 0. Again, if I have T1 here and I have T2 here, we can see that T1 will be T2. We can see that. In calculus, we'll calculate using the area under the curve, and you can see the area is almost the same. Any other questions? Can I go to acceleration versus time curve? Acceleration versus time curve. Remember I said upward is positive. Upward is positive. And I said acceleration always acts downward. That's what I said to you. It's constant. I'm going to have something like that. Right? I have time here. The second, I've got the acceleration in meters. Second. I said it's constant. It's constant. So what's going to happen essentially, we're going to say zoop. So at time 1, acceleration will still be g, 9.8 meters per second. At time 2, acceleration will be g. Do you guys understand? So here you can even write the value, 9.8. So that will be my acceleration. Any other question? Do you understand? So at T1, if I have T1 here, acceleration will still be 9.8. If I have T2, acceleration will still be 9.8. T3, acceleration will still be 9.8. Acceleration is constant, it doesn't change. But please note, this only applies to anything that is moving closer to the center of the Earth. Closer to the center of the Earth. For motion of rockets, we'll see as we continue with physics. For the motions of rocket, for the motion of the plane, it does not apply. What I've just said does not apply. But under your scope of work, you are dealing with anything that will be projected nearer to the center of the Earth. Now acceleration or constant becomes constant at that point. Are there any other questions? No. Good. Now we are going to have a session of equations of motions, and we are going to do some application.